Welcome to AI Podcast. Today we're digging into a NeurIPS 2025 paper called SWE rebench, and the short version is this. They built a fresh, automated way to gather real software engineering tasks and a cleaner benchmark to test coding agents, and when models face those fresh tasks, their scores drop compared to older benchmarks.
So bottom line first. Fresh problems, lower scores, more honest picture. Who made this?
The work comes from the Nebius research team. Think lead authors like Ibragim Badertdinov and Alexander Golubev, along with a larger crew.
Got it. Now set the scene. What was broken in the status quo?
Two big pains. First, training data for agent-style coding is thin. Most data sets are single-shot code prompts or small hand-curated sets, not the messy interactive stuff agents actually do. Second, evaluation has been drifting. Static benchmarks get famous, end up in training mixes, and over time you get contamination. On top of that, teams compare results using different scaffolds, prompts, and retry tricks, so numbers don't line up. And because agents are stochastic, a single run can be lucky or unlucky.
Right, I've seen that movie. You think you're comparing engines, but you're also comparing car frames, tires, and tailwinds.
Exactly. SWE Bench and its verified subset kickstarted this area, but they're static snapshots. Helpful but not ideal for gauging true generalization today.
So what's the pitch with SWE rebench?
The idea is simple but ambitious. Continuously mine real GitHub issues that were actually fixed by pull requests, build a runnable environment automatically, and then evaluate models with a standardized, minimal agent scaffold. On top of that, filter by time so the test set post-dates a model's release, which makes contamination less likely.
Time filtering is decontamination, like testing a chef with ingredients they couldn't have prepped yesterday.
Perfect analogy. If the recipe only arrived today, your prior training is less likely to have memorized it.
How do they actually collect these tasks?
Pipeline in 4 moves. First, they scan GitHub events and repos to find issues that were resolved by merged pull requests. They keep Python repos with permissive licenses, and they require that the pull request modified or added tests, which is crucial. You need tests to automatically verify whether a patch really fixes the issue. Second, they auto-generate installation instructions. An LLM reads files like README and setup tooling to draft a structured install recipe. Third, they run everything in containers and verify the logic. Before the patch, new tests should fail. After the patch, those tests should pass, and passing tests should keep passing. Finally, they attach quality metadata, like whether the issue is clear and whether the test patch looks correct using an LLM-based assessor.
So everything from problem discovery to environment setup to pass-fail checks is automated. How big did this get?
The public dataset has more than 21,000 executable Python tasks drawn from roughly 3,500 repositories. For the paper's reported benchmark slice, they used about 300 tasks to keep evaluations manageable while still diverse.
And the benchmark piece, what did they standardize?
They fix the agent scaffold and prompts, run each model multiple times, and report both the average resolved rate and pass at 5. The important bit is comparability. Imagine a wind tunnel for coding agents. Same airspeed, same angle. So you see the wing, not the paint job.
Nice. Which models did they look at?
A mix of proprietary and open source families. Think GPT, DeepSeek, Llama, Qwen, Gemma, and so on. The key is not who won, but how scores move when you switch from old static data to these fresher tasks.
Okay, so what moved?
On the time robustness check, they compared a January slice to a March to April slice. For example, GPT 4.1 dipped from around 31% resolved to about 27% on the newer slice. And when they compared against SWE bench verified, they saw bigger gaps for several open models. One clear example is DeepSeek v3, roughly 40% on verified versus about 21% on SWE rebench's fresh slice.
That's a big step down. Does that prove contamination?
It's stronger as a signal than a verdict. Time-based decontamination plus performance drops is suggestive, but it's indirect. To prove contamination, you'd want document-level overlap analysis against pre-training corpora. Still, The evidence lines up with the story that static, well-known benchmarks can inflate results over time.
How do they interpret pass at 5 versus the average resolved rate?
Pass at 5 captures whether the model often gets a correct solution within a handful of tries, even if it's inconsistent. There's an interesting case where a model shows a relatively high pass at 5, but a modest average resolved rate. That pattern says the capability's there, but it's unstable run to run.
And the LLM assessor that labels issue clarity and test correctness, how much should we trust that?
It's useful at scale, but it's still an LLM classifier, not a human panel. The authors acknowledge the accuracy isn't perfect. As a filtering knob, it's helpful. As ground truth, you'd want occasional human audits.
Reproducibility-wise, any hidden gotchas?
The pipeline is heavy. They rely on distributed infra to build containers and run tests at scale. The code and dataset are public, and the evaluation harness is standardized, but recreating full throughput needs real compute. That said, for using the dataset or running the provided benchmark slice, you don't need a data center, just patience and good caching.
Language coverage is Python only, right?
For now, yes. The approach is language agnostic in principle, but the release focuses on Python. Expanding to Java, TypeScript, Rust, or Go would be huge for generality.
I'm curious about the standardized scaffold choice. If you fix a minimal agent loop, does that understate models that shine with richer tool use?
Fair point. The author's goal is model-centric fairness, so they keep the harness simple and uniform. That's great for apples-to-apples comparisons. But in practice, many production agents lean on tools. A parallel tool-heavy track would complement this nicely. And the project site already supports a terminal tool mode, as well as a text-only mode, so the path is there.
Let's make it concrete for a listener who builds internal evals. What should they copy tomorrow?
3 things. 1, adopt time-based slices for your evals so last month's tasks are separated from next month's. 2, standardize the harness and prompts and run multiple Cs so you get confidence intervals, not just a single lucky run. 3, feed the agent real issues with executable tests, not just toy snippets.
And if they want data for training those agents?
Use the dataset. It's big, it's executable, and it's annotated. It's like moving from practicing free throws in an empty gym to scrimmaging with referees and a scoreboard. You get feedback that matters.
Quick reality check. What are the main limitations I should keep in mind?
The benchmark slice in the paper is a few hundred tasks, so it's not the whole dataset and not every domain. Labels from the automated assessor carry noise. The compute cost of end-to-end reproduction is non-trivial, and a single fixed scaffold won't surface every model's best case.
And future directions?
Grow beyond Python. Scale the public benchmark slice and report per category breakdowns. Add a tool-rich track next to the text-only track. Do deeper content overlap checks to strengthen the contamination case, and keep periodic human audits to calibrate the automated labels.
All right, give me the takeaway our listeners can quote.
SWE rebench shows that if you evaluate coding agents on fresh, real issues with a fair and consistent harness, the scores are tougher but truer. It turns benchmarking from a memory test into a road test.
Tougher but truer. If you want to see the live leaderboard or grab the dataset, search for SWE rebench. It's all public.
That's it for today on AI Podcasts. Thanks for listening, and as always, send us the papers you want us to unpack next.